Yeah. So welcome everyone. Today we're very happy to have Tom Faulkner from UIUC who's going to tell us about asymptotically isometric codes.
Okay, thank you very much. So I'm going to start, unfortunately. Oh goodness.
Use the video.
Sorry. It's some math. Sorry. Okay, so this is some math prerequisite. So I need to get this out of the way because I'm going to assume a bunch of this stuff. And I don't know how familiar it is to everyone, but there's some things that are sort of maybe quite technical, but there are technical aspects of these codes that I'm going to talk about, and I think they're actually related to some important physics. So, but let me just start with the math. Okay, so in finite dimensions, we have a Hilbert space, for example, and we have operators on that Hilbert space, the linear operators, and we have various norms for these operators. Okay, so the natural one is the one that I'll just denote by the usual norm, which is the maximum eigenvalue of the meg of the sort of the positive part of A. And the one norm is just the trace norm, and so forth. And if we want to take limits on these operators, so for example, I want to say the sequence of operators limit to some other operator, then we'll do it in various norms. Right? We pick a norm and say, well, that means that goes to 0. And in finite dimensions, there's sort of norm equivalence. So because there's these relations between these norms, there's ones that work even in infinite dimensions, but then I come back to myself by including a factor of the dimension here. So if I'm just taking limits, I can use any norm and it's fine. Of course, physically, we have errors. And some of these errors might scale with a dimension or something like this. In which case we no longer have normal equivalence. Okay? And so there's sort of subtle things that happen because of this, and it's quite common. In this talk, I'm going to sort of ignore this way of thinking about it and think about this problem in a different way, where I'm always going to be working in infinite dimensions. And in infinite dimensions, you do not have normal equivalence. So if I have some operators B of H, so these are bounded operators on the Hilbert space, I have to say they're bounded down because we're in infinite dimensions. Then I can say, sequences of operators converge like this if their norms converge, that's called uniform convergence, or if their matrix elements converge. So if I just take matrix elements like this, and all of the matrix elements converge to 0. So it's important here that I sort of fix the matrix elements beforehand, and then I take the limit. And similarly for the strong, so this is the weak operator limit, and this is the strong operator limit. The strong operator limit, I just fix one state and I compute the Hilbert space norm. So this is the Hilbert space norm. And I do that for all states in the Hilbert space. And so you have the equivalence that if I have norm convergence of the sequence of operators, then it implies strong operator convergence. Yes?
What you just said, you weren't committing to any particular norm.
No, I haven't committed to anything. I'm just telling you the options, okay? In this talk, we'll essentially focus on these things here. But again, there are other things we can talk about. Now, of course, if I have non-convergence, that implies strong operator convergence. You can just prove that, and that also implies weak operator convergence. But there's no converse, so I have to pick one. Be careful about which one to use. And so this is sort of this issue coming back, but now sort of thinking in infinite dimensions where we can't, these limits are just never equivalent. Right? So I can have a sequence of operators where the matrix elements converge, but that doesn't mean that the norm of the operator is converging. Okay? In this context, we define von Neumann algebras, which are going to be important, so I thought I'd just sort of get it out of the way. Von Neumann algebras are some subset of operators, some subalgebra of operators of all of the possible operators. So B of H is of all possible operators that you care about. You take some subalgebra, and then you make sure that it's closed in some appropriate topology. It turns out it doesn't matter which one you use, as long as it's one of these two and not this one. Okay? So you use strong or the weak, but not the uniform. And then you define what a von Neumann algebra is. And then there's a much nicer way to define what a von Neumann algebra is, which is just to say that it's equal to its double commutant, where the commutant is just a set of operators that commutes with A, a set of operators in the Hilbert space. Okay? And in this context, we talk about states on the von Neumann algebra. I'll sort of switch between talking about just vectors as states, and the way that sort of mathy operator algebra people would say, talk about states, which is that they're just linear functionals on the observables, right? So n are going to be my observables, and to each observable I assign a complex number, okay? And I have to make sure that it's positive, so when I put in a positive operator, I'll get a positive number out. It's normalized, and there's some appropriate continuity that I want to really talk about. Okay, so that's the math prerequisite. Now let me say some physics. Leave it there so you can stare at it. So I'll just say something about physics of von Neumann algebras. So physically, sort of, the n that I've defined in this way are sort of the observables that are well approximated in experiments. So in particular, if I allow experiments with some errors, then it's quite natural that you get this weak operator topology, which is defining the closure of the von Neumann algebra. So it's quite natural. This is a natural class of observables from that point of view. Of course, this is still idealized, because to measure any of these matrix elements, I might need like an infinite, or not an infinite, but a large number of copies of the system, and I need sort of arbitrary control, or good control on the experiment. Okay. Now, in quantum gravity, there's good reason to expect that we might be limited in what kind of experiments that we can do. So we expect experiments limited at finite G Newton. And so maybe we can't measure something for an arbitrary amount of time, or we can't have a large number of copies of our system. So that means that, in some sense, we have to confront this technical issue of what kind of convergence we're talking about and so forth. Okay, so that's motivation for this. Another motivation, of course, is if we sort of try to approximate Hilbert spaces of finite dimension, it's quite natural. For example, the black hole Hilbert space scales like e to the 1 over G Newton. So that's scaling with G Newton, which is the parameter that we're taking small. So that means you don't have to worry about this issue in finite dimensions. Okay. Good. So given that, what I plan to do today is to study these kinds of issues in a concrete model of quantum gravity and ADS-CFT. Okay. So we're going to concrete study these issues in ADS-CFT. Okay, so the context for this is I'm going to imagine that I have at my disposal an ADS-CFT duality. So I'm going to think of this as CFT, or really a sequence of CFTs labeled by a number n. Okay, where n is just going to be natural numbers, say. And so for each n, I have a specific CFT. And of course, it's good to have something in mind, e.g. some Yang-Mills theory with SUN and colors. Of course, in this context, we also know that if there is a duality, then G Newton is going to be proportional to 1 over n to some power. Okay, so as I take n large, G Newton is getting small. Okay, and so these sequence of CFTs act on a sequence of Hilbert spaces that I'll call kappa n. And I'm going to take them to live on the cylinder, CFT, so we can do that, which I'll just call K. So here's my cylinder. And I'm going to think about this particular CFT in an algebraic quantum field theory language, okay? So it's not, so that's the language that I'm going to use. So what does that mean? It basically means I'm going to think about locality in the CFT in the following way. Associated to causally complete regions that I'll call O. There's an assignment of von Neumann algebras. Depends on O, and these are subalgebras of all possible operators that act on the CFT Hilbert space that lives on the cylinder. Okay, so there's these causally complete regions, and to each causally complete region I have another causally complete region called O prime, which is just a set of points in K that are space-like separated to O. So I can draw a picture if I unwrap the cylinder, just identify this with this. Here's my original region O, and then I have O prime. This. Okay.
So can you say again what the things are on the top right, MN, O, and UKM?
Yeah, good. So this is an assignment given a causally complete region of a von Neumann algebra which is a subalgebra of all operators. So this is the algebra that is accessible, in this causally complete region.
And why this? So MN, O is just the von Neumann algebra associated with O, the usual algebraic one.
Yeah, that's right.
What do the letters M and N mean there?
Ah, good. Yeah, because I'm going to try to parameterize everything that depends on N. And M is just a label for the algebra.
So N is just the subscript of the CFT.
Yeah.
And then there's a curly N, which are your observers.
Yeah, that's symmetric.
Okay.
Is that HN or KN?
This is KN, kappa N.
Oh, kappa.
This is kappa.
Why kappa?
I don't know.
It's a Hilbert space.
Yes.
It's a Hilbert space.
Yes, it's a Hilbert space. Yeah, this is the Hilbert space.
And this is the Hilbert space associated to the whole.
The cylinder. So the CFT of the sphere. So this is SD minus 1.
And your observables are Hermitian operators, self-adjoint operators.
No, they don't have to be.
Yeah.
Yeah, of course, it's quite natural to take self-adjoint operators, but okay, so good. And so this is a natural region, and we also have an algebra assigned to that region. Okay. And now, in this context, we sort of assume various axioms that these algebras should satisfy. For this sort of finite N theory, I'm going to assume all the reasonable things that you would imagine. Okay, so there's a list of these, so I'll write some of them, but this is not all. So reasonable conditions. The first one is that MNO should be locally generated. So that means that if I take O, my causally complete region, and I cover it by smaller causally complete regions, right? I'll call these diamonds. And this is meant to be a complete cover, but I won't draw it. Then this should be the same as the algebra that I get just by taking the algebraic union of all of these diamonds in the cover. This is the diamond. And this is very natural. It just means that it's locally generated. The algebra is locally generated.
I thought that something stronger than that can actually be proven for von Neumann algebras.
it can be proven, certain stronger things can, yeah, so I will write a stronger thing in a second, but yeah, so they usually require some other axioms, like the symmetry or something like that. This is not a property of the von Neumann algebras, right? Because, just abstractly the von Neumann algebras and algebra, this is really an assignment of algebras to regions. So you could have various things going on, and we'll see some examples where we don't have certain strong conditions that you might have expected.
What is it that you're not assuming that, for example, goes into the time-like two theorems?
I'm assuming everything that would go into the time-like two theorem.
And doesn't that theorem already vary about the
Yeah, sure. Yeah. So I think what you're getting at is the axioms that I'm going to write down are not. Some of them imply other ones, right? And I don't care. I just want to give you the properties.
Oh, you're saying if you assume this weaker statement, then you can derive from that the stronger statement of the time-like two theorem.
Yeah, sure. Something like that.
Thank you.
Yeah. So I don't really care about those details for the boundary algebra. I'm just assuming really nice things. All the nice things you might expect. So the other thing, which is a bit more subtle, is called hard duality. And it's a relation between the algebra of the space-like separated region and the original one. And it's this relation. So if we just had causality, right, operators here should commute with operators here, the only thing you could conclude is that this should be a subset of this. The strong statement is that you have equality, and this is called hard duality. And it's completely, if you were thinking about quantum field theories, regularizing them on a lattice, then this is a completely reasonable thing. If I just have some, if I just assume the Hilbert space has a tensor product factorization between two regions, A and A bar, so these two regions might have been sort of A and A bar here on this slice, then you just automatically have hard duality. This assignment is automatically hard duality. So this is kind of a reasonable thing to assume. Okay, good. And then the other thing that that I'm going to assume, but is also something you can derive based on various conditions, is that these are a special class of von Neumann algebras called type 3-1 von Neumann algebras, and they're hyperfinite. Okay, so it's not really needed the details of what this means. They're just some non-trivial von Neumann algebras that exist only in infinite dimensions. Okay, and so this is the setup. And so now, in this context, I want to model the bulk theory, and I want to do it in the limit as n goes to infinity. Okay, that's the goal. Getting rid of the math. Okay, so we're going to model bulk theory in the n goes to infinity limit. And this is sort of the semi-classical limit, g goes to 0. And often you think of the n is equal to infinity theory as being determined by a special class of fields called single trace fields. And so if I take a particular example, we don't need to work with this example, but if I did take this example of Yang-Mills theory, assuming Yang-Mills theory, there's a nice class of operators that just like trace of the fundamental fields, just one trace, called single trace fields. And they're nice because they exist in each of the n theories, right? So it's something that then allows us to take the large n limit, right? They exist in each of the n theories, so then we can take a limit off. And that limit, of course, is then somehow determined by these single trace fields.
How would we know that Yang-Mills is locally generated? Like, it's not obvious with the non-abelian gauge theory how to like build a large Wilson loop out of a little Wilson loop or something like that.
I think if the region is topologically trivial, you can do that.
Like,
So if the Wilson loop is contained in that region, then you should be able to locally generate it.
but it's not a simple matter of taking a product of individual Wilson loops, definitely. Which would be a median.
Well, you know, if you think about it as, you know, taking the Wilson loop and contracting it to zero, I expect there's some PE expansion and the fields in that will be, so it's some version of that, I think.
Yeah. Oh, I'll definitely believe it. I'm not claiming to believe it, because I'm interested in how well it's named.
Yeah, okay, I don't know, I'm going to assume it, but yeah. Okay, so, good. Okay. And in principle, we'd like to do this and then include, say, 1 over n total expansion. But you know, if there is a perturbative expansion like this, we don't expect it to be convergent perturbative expansion. So there's always a sense in which this is some formal expansion. So this is some formal thing where there's some parameter. We should think of the using complex numbers as generalizing complex numbers to the ring over this formal parameter. So in principle, you can do that. I'm not so interested in doing that just because I want to start off just by studying the n equals infinity theory and doing that really well, and then maybe later on we can come back and do this.
What do you mean by this ring?
What's that? I just mean if you want to understand this perturbative expansion as some kind of, in some algebraic language, it's quite natural to think about it as just like a formal parameter that you sort of you have around, and then you just have polynomials of this one or this formal parameter, and that everything is valued in those polynomials. So whenever I do a calculation, there's going to be some order 0 term or whatever n term.
This helps you with non-convergence of this?
Yeah, it means you don't have to worry about non-convergence.
You just worry, the point is that you don't add up the terms, keep them separate.
Yeah, exactly. Yeah. And you don't pick a particular value for whatever n or anything. Of course, at some point you can, and then you can see whether it approximates the answer, and it probably will, but it won't be a convergent series. I'm not going to do this. This is an aside. Okay. So, given that, what I want to understand, what I want to motivate for understanding the sort of infinite n theory is the following structure. So, we're going to have some bulk theory that's determined by some Hilbert space H. So this is like this is determined by the symmetric fields. And you should think of it as the infinite n theory. It's like the infinite n theory. And then I'm going to think of this as some kind of code subspace in the language of quantum error correction. And then also in the language of quantum error correction, I'm going to think about the finite n theory, where I just have a fixed n, kappa n, Hilbert space, as the physical theory. So this is the code subspace, and this is the physical theory. And then we need some map between these two. And encoding map, which is a sort of encoding map, perhaps familiar from quantum error correction. Okay. And so already there's an interesting feature about this code, this structure that I'm defining. The code subspace is the infinite n theory, and it's used as a code subspace for the physical theory at finite n. And I think this is very natural if you think about it from this point of view. Perhaps we do want to include perturbative corrections, but even if we include perturbative corrections, we're working around the infinite n theory, so this is still a very natural setup. Okay, and So in this context, we have this Hilbert space, and we're going to have polynomial algebras, again assigned to boundary regions O. So to each O region, I'm going to have some polynomial algebra, and this is going to be a subalgebra of H. Okay? And so this is a similar algebra field theory setup. Right?
Why is the phenomenon algebra not called C and it was MN over there?
Because this is of the bulk theory, and that was of the boundary theory, and they're different. So they're different, and they're constructed in different ways.
So here, O is a bulk region?
No, O is a boundary region. I'm still going to assign algebras to the boundary region. But it will correspond to, in ADS-CFT with a classical gravity dual, it will correspond to some causal wedge in the bulk, which it has a natural geometric region. But I don't really want to bias myself by that. So I'm just going to assign algebras to boundary regions.
But afterwards, C is going to be some operator in the entanglement wedge, or like?
No, it'll be the causal wedge. So I'll go through that. I'll sort of explain how you should think about each of these things. But for now, it's just some assignment of polynomial algebras to the boundary regions. Okay, and so this is two of the things that we need. The final thing we need is a set of maps that takes us from the bulk algebra to the boundary algebra at fixed. And as we'll see, these can be interpreted as the simple reconstruction maps. And at this level, you can think of them as really just a version of the extrapolated dictionary. Right, so in the extrapolated dictionary in the ADS-CFT, we have some bulk geometry that fills in the cylinder, and then we have fields in the bulk, and if we take them near the boundary, they correspond to operators in the boundary theory. And so this is, if I just think about those operators here, then this is that.
H, capital H was the boundary theory at infinite n.
Yeah.
So the C doesn't have a subscript because it's also.
Yeah, so exactly. So if it doesn't have a subscript, it's kind of the infinite n theory.
And they can believe this is okay, bleeding over. Or you say something like, even without degree 1 by n, maybe okay or something.
Yeah, I think it should be okay, but I honestly haven't thought about it to the level of actually writing something about it. Yeah, I've thought a little bit about it, but yeah.
You should do probably defining Hn and
Yeah.
between and decay.
No, yeah, I wouldn't think of it that way. I would think of it as a formal thing over this 1 over n parameter, right? And maybe to make it clear, I would call that parameter something else, and then in some way, then I assign it to be equal to 1 over n when I do this math. Something like that.
Yeah.
Yeah. But I think that's important, right? So it would be a formal extension, but okay. But let's not do that.
What about Hilbert spaces over a power series?
Yeah.
It's more confusing than algebras over a power series.
Yeah, that's true. Yeah, I probably shouldn't have done it here. Yeah, I should have done it here. You're right. Yeah. Although there is some construction for that. Yes.
Is C of O a space of operators in the bulk or in the boundary?
It's a space of operators in the bulk Hilbert space. Although, I'm biasing my language by what we expect, but really, the setup is very general. It need not, this sequence of theories need not actually have a gravitational field, in which case I will still be able to define this algebra. Okay, so together, so then these sort of things that I've defined, given you as a triplet, there's these maps between the two Hilbert spaces, there's the bulk operators, and then there's these reconstruction maps. This defines what we call an asymptotically isometric code. And they satisfy, together they satisfy some nice properties. We need the weak operator limit of Vn dagger Vn is 1 on the bulk pivot space, and the strong operator limit of these reconstruction maps act as reconstruction maps. So this is part of the structure, this assumption. Yes?
Normally I would have thought that your gamma n is like operator quantum correction, and
Yeah.
Vn is like one, like, doesn't that encompass the Vn already in some sense? Or is it separate?
You're right, it does. And in fact, you can derive this structure. From just starting from some assumption about the existence of single trace fields and some nice states that have nice limits. You can just go ahead and derive this structure. And in deriving that structure, you actually construct Vn from gamma n. So they're not entirely independent. I mean, these equations link them, but I think it's useful to put them as separate entities in this construction.
So the reason you're using weak operator limit for the strong operator?
In this equation?
Yeah.
No, not really. It's the weakest thing we can do and still get results. It could be the strong operator limit. In fact, in this derivation in quotes, which had some assumptions, we actually derived it as the strong operator. So it plausibly could. So at some point, if you need the strong operator limit, that's totally fine. But we can still get a lot of results assuming the weak operator limit.
So just like those, these are definition of the ball or something.
Yeah, so this is a definition that I'd like to give, and I'd like to say it's well motivated, both physically and because we can almost derive it from an assumed duality. So
you don't claim that it just completely derive this.
Yeah, so there's some technical assumptions about the convergence of some limits that we need to make to derive it. So it's not a derivation, we have to make some assumptions. They may not be true, but I think it's motivated, and I think they probably are true.
So this is the starting point of your research.
Yeah. So now I want to say, let's just study this structure, okay? And try to get some things out of it. But let me just say something about the physical motivation. And I just want to focus on this weak operator limit, the physical motivation. Is this question about like what observable, what experiments we can do in quantum gravity? The idea in this code is we should sort of fix the experiment. So for example, an observable C and then a state or two states in the Ball-Kilbert space. And then once I fix these, for sufficiently small G Newton, we expect this code to give a good approximation to the outcome. So I have to fix the observable, right? So it could be a pretty complicated observable, in which case G Newton has to be really, really small. But there's some G Newton at which it will work.
This isn't supposed to be restricted to the vacuum sector, right? I could do this in ADS with a neutron star.
Yeah, you could do that. As I'll say later, I think there's a whole family of codes. So you have to fix the classical solution and work around that.
Yeah, what I'm asking is, as you scale G Newton, is there some canonical way to think of the quantum state of the neutron star that's going to be whole dimensional?
I have to think about that particular case, but I think so. Yeah. So if there's the neutron star has some back reaction, so then I think it would be a different code. Like it's like you could start with AES and then act with a bunch of operators to add fermions or something, and then eventually it will form a neutron star. But the number will have to compete with n, right? So that sort of goes outside of this code.
I mean, it's not obviously like in the real world, for example, with QCD as it is.
Yeah.
We just dial G Newton that we could find solutions that would hold the metric space. I think you're just working around a different background. So I think
that's okay. You're worried about, wait, what are you worried about?
Well, I thought that what you wanted here is for the background to be the same at every value of n.
Yeah, that's what,
And just the Planck length to scale. But if in strongly coupled systems that are gravitationally bound, that can be hard to do.
okay, yeah, okay. All right, good. So let me think about those cases. We will talk about it later. About those cases. Well, yeah. So I think it should be okay, but we'll see. Yeah. Okay. So yeah, I'll say a little bit more about this hopefully at some point. And then, yeah. Okay. So I want to study the structure in general, but let me make a few comments about what we expect. So some expectation. And maybe some things that you already know and how to fit them into this structure. Okay, so one thing to point out is that C of O can be a non-trivial unknown algebra. Because the bulk Hilbert space is allowed to be infinite dimensional, so this could be type 3 unknown algebra, it could be type 2 unknown algebra, it could be all sorts of things. In general, when we derive this code, there's nothing that tells us that we should have high duality for C. So it's not something that I'm going to assume. So high duality would say this is an equality. Like the algebra operators in O is the same as the commutant of the algebra operators in O prime, or associated to O prime. And so this need not be the case. So high dual violations. But I still expect C of O is additively generated. Right, so if I take a diamond cover of O, I should be able to generate C in this way. It's still active. And again, you can derive that. You can derive these codes.
I'm a little bit confused about which things you claim you're deriving and which things you claim you're assuming here. Can you say that again?
Yeah, so I'm going to assume these things, and the motivation for assuming these things is that we can derive them in some codes. Okay? But the things that I'm assuming are very weak. So this is microcausality. This will always be true. I'm not assuming equality here. That would be a strong assumption, which I think is wrong. I'm going to assume that it is additive, and there's some motivations for that. So let me say what those motivations are. Yeah. So if I draw, so let me draw some pictures actually for these two things. So C of O. So let's assume we have some kind of semi-classical dual. So I can draw pictures. Then I have just a fixed time slice. Now this is the bulk of the space-time. And associated to some boundary region O, I have some algebra of operators, which is then some algebra of operators in some bulk region, C of O. And then associated to the complement region is an algebra of operators. And these need not be equal. And so this is C of O prime. And so the existence of this region is related to high duality violations. Okay. The additive property, let me draw a different picture where I just put the boundary at some fixed slice here. And then I draw my causal diamond here. Then there's a natural region associated to this causal diamond, which is the causal wedge. So this is some region that comes out here. This is the causal wedge. And the fact that this is locally generated means that I can replace the algebra operators by just operators in smaller diamonds near the boundary. So when the diamonds are small, they're near the boundary. Right? And that's sort of where you do the extrapolate dictionary. But then it's a one-nomen algebra, so it's equal to its double commutant. So that means that it should be naturally associated to a causally complete region, and the natural thing is actually not the causal wedge, it's something that's slightly larger than the causal wedge. We'll call it the causal domain. The causal wedge is not necessarily a causally complete region, so there's a slightly larger region that is, and so we're going to associate the algebra C of O to that region.
Shouldn't it be called the other way around? I feel like we've sort of standardized on wedges meaning causally complete regions, say. We should like rename
Yeah. I talked to Veronica about this and she wanted to name it something else. Maybe she gets the name right.
Sorry, this union, this algebraic union that you wrote down there.
Yeah.
I thought that was supposed to, in your earlier example, I thought that was supposed to run over like smaller wedges that actually cover some kind of closure slider.
Yeah. So I defined it to be a cover of the boundary region. So the boundary region.
Boundary region, sorry.
Yeah, so it's a boundary cover of the boundary region. Okay.
I see.
And so actually to establish something like this, I need some version of HKLL. Or the modern way to think about it is the time like tube theorem, which just says that if I know what's happening, if I know all the operators near the boundary of this causal region, then I can generate all of the operators in the causal completion of that, which is this causal domain.
And in your upper picture there, this gap between the two causal wedges, is that just supposed to be, am I supposed to think of entanglement wedges being larger than?
Yeah, that's right.
That's all that is.
So the existence of this violation could lead to non-trivial entanglement wedges.
But in light of Jeff and Chris's refinement of the entanglement of max and min, how does that come into your picture? Is that something you want to comment on later?
Let me just say something right now. It's not allowed by these limits. So we're taking really strict large N limits. I think to do that, you have to take a different limit. It's a good question. Actually, I should define that.
QES is a trivial even here, right?
What's that?
You're taking a limit where everything's determined by the classical geometry.
Exactly.
HRT.
That's the limit I want to take. Because I'm taking this strict large N limit, that's what you expect. I don't know if that means that you can't get it. Actually, let me take that statement back. I'm not sure if there's situations where maybe this could be this max entanglement wedge or something, or this outer wedge. But yeah, for now I'm going to not assume that. So because it's just we're taking the strict large N limit, we don't have to go through this.
Still not here over there.
I'm not sure if it's happening. I can comment on that later. So okay, good. So let me keep going to say some things that we've proven in the structure. So
can I also very pedantically object? You said that the time-like tube theorem was a modern version of HKLL. Weird chronology.
That's fine. That's fair enough. If you had read what's his name's paper?
Bushes or whatever. Iraqi.
No, that's right. But the fact that it's related to AES-CFT is quite old, right? In this paper by, I forget, one of the algebraic quantum theory people, they made this observation right in the background.
Raren, maybe.
What's that?
Is that Raren?
Yeah, Raren made this observation. Right, and I thought that paper was crazy, so I didn't look at it in detail. But if you had, then...
You really missed the bigger point in an annoying way.
Yeah, that's
it
right.
seems like we should have paid attention to the smaller point.
Right, exactly, yeah. So anyway, okay, good. So we have this. Now, okay, entanglement wedges. Everyone wants to know about entanglement wedges. So I'm thinking of entanglement wedges as extensions of the causal wedge. So here is my causal wedge, and maybe I want to extend it a little bit. Okay, I want to extend the complement causal wedge a little bit. And I can do that as long as I can still reconstruct operators in this region on the boundary region. Okay? So if there exists a quantum channel, well, just a map, let's say, on Neumann algebras in the bulk region, this extension to the boundary region, such that this reconstruction statement, in terms of the strong operator limit, still applies. Okay. So if I can do that, then I can extend the region I associate to the boundary region. And that extension I'll call E.
Are you defining it as the largest feature with this property?
Yeah, I should when I talk about the entanglement. So let me say this is like the reconstruction wedge, and then the largest one. Yeah, so it will be called an entanglement wedge if I can make it as large as possible. So yeah, so I'll get to that in a little bit. But this is, for now, I'm just talking about the extension. So I just extended a little bit. And this is an assumption. This I don't know how to derive in general for general code, but I'll say some ways that you can derive the existence of these extensions. Later on.
So what is the difference between this? Is it the simple reconstruction maps no longer applicable? Or?
Yeah, that's right. So this is like a simple reconstruction. It comes but in the definition of the code, and in the construction that we have, it's really simple. Right?
What's the technical definition of simple here?
I can write down an equation. One line. So it's not a great mathematical definition, but it's very simple. Like, it's simple. I can really write it down. Yeah. And it doesn't involve density matrices. Perhaps I should say that. Yeah. Okay, so this is the extension, and so now we prove. This is an assumption, but given such an extension, we can prove some theorems about them. So this is the first theorem, which I'm not going to go into detail, but basically says that the bulk maintains boundary causality. In math equations, it says that this extension for O has to be contained in the extension for the complement region, the commutant of that. Okay, this may not be so. I mean, this is causality, as I said before, but it takes a little bit of time to wrap your head around. All this is saying is that an extension like this is not allowed, right, where I can both extend here and here, there's an intersection. Okay, so that's the first theorem. And the second theorem pertains to maximal extensions. So if I can extend C and C of O prime so that they're equal to the commutants of each other, then I can prove the condition under which that's true. These are well-known conditions, but you derive them in this context. So, theorem 2 pertains to maximal extensions. And this is the version of the theorem theorem. So, and it goes as follows. The following are equivalent when you give two conditions and they're equivalent to each other. Right? You have to assume one of them to compose the other. So the first one is the extension is maximal, which means that it satisfies hyperbola. Right? Which means in this picture that here, the extension goes all the way here and all the way here. That's the first condition, and the second condition is that for all states on P H, on the Borel-Hilbert space, the limit as n goes to infinity of the relative entropy of these states pass through the channel. That's what this adjoint action does. It puts the states from the bulk onto the boundary. Sigma adjoint Vn restricted to the boundary region Mn of O is equal to the bulk relative entropy of these two states restricted to the entanglement wedge. Okay, so this is just an asymptotic TLMS. If I can take a limit of the relative entropies, as n goes to infinity, there's all n's here, there's no n here, and it's equal to that relative entropy for all states, then I can conclude that the entanglement wedge is maximal. There's some technical things here. I need to smooth this relative entropy in some particular way. And this is not really all states, but some reasonable class, a sufficient number of states with some conditions. Like this. Okay, but then this is technical. But essentially, this is all the same.
More of the techniques used to prove this are just like the sort of old ones to prove equivalence.
Yeah, but there's some super powerful results of that relative entropy that I've never used before that came up, which is this, you use this lower semi-continuity of the relative entropy under this super weak convergence, which is just pointwise convergence. So when we talk about states being reconstructed or operators being reconstructed, everything here is sort of pointwise.
Fix
an operator and then you take the limit. Yeah. And if you have that, you still have lower semi-continuity, and that's sufficient to prove. So yeah, that's an old. There's some old papers by Pets that actually has a similar structure that does that. Okay, so good. Okay, so now I get to say some new things. So this is sort of preliminary. This is kind of a new result, but it's not published.
So up till now it's all in the paper.
Yeah. Okay, so the new result is okay, so the first new result is that there's an equivalence. Okay, so there's sort of two paradigms for doing bulk reconstruction that have been put forward. There's the quantum error correction approach, which Jeff has pioneered a lot of. And then there's this other method, which is due to Aitor and I, which is the modular flow reconstruction, which is a bit ad hoc, but there's some other way of doing entangled reconstruction. So the new result is that you can prove in these codes that these are equivalents between, let me say, QEC and modular flow reconstruction. And it follows from the following assumption. So if I assume there's a vector in the Hilbert space, this is a very reasonable assumption, but it's the key point to this. I assume there's a vector in the Hilbert space, so I'll call eta, such that it is cyclic and separating for both the causal wedge and the entanglement wedge. So cyclic just means that if I act with all the operators C on eta, I get the full Hilbert space. Separating means that if I act with some operator from C on eta and I get 0, then C has to be 0. So this is some conditions that express the fact that the vacuum is, or this state is very highly entangled. So if you have this for both of these algebras, then there's a third condition that I can add to this theorem, which is equivalent. I'm going to add a third condition, which is just that the, let me write it over here. The third condition is that the following limit applies the strong operator limit of modular flow of the boundary theory acting on the causal wedges construction modular flow. So this is n goes to infinity. So modular flow, this is a sort of a symmetry of the algebra. It depends on a state. And this is modular flow for the algebra Mn, the boundary algebra, for the state En eta, which is the state you get by mapping it through the code. And this is the modular flow for the entanglement wedge in eta. Then this is equivalent to this, okay? So if you like, these conditions here are like reconstruction, they're maximal reconstructions on both the entanglement wedge and the complement. And this is the condition that the modular flow of the boundary region acting on simple reconstructions is the same as the modular flow in the bulk. Okay? So this is the essential condition that Aitor and I use to do bulk reconstruction. And to go from here to here, you have to use a similar method that Aitor and I used. In particular, it uses the following result that we didn't know at the time, we basically assumed. If we have a state that's cyclic and separating, jointly cyclic and separating like this, then if I take the algebraic union of the modular flow with respect to E of the causal wedge, and I generate the full entanglement wedge. Okay? And so perhaps that's not so crazy, but
what's the sort of strategy to prove that without going too much detail?
This algebra is invariant on the modular flow.
Yeah.
So that means there's a conditional expectation between the two.
Okay.
Joint cyclic and separating rules out, says that the conditional expectation is trivial. Yeah, because the existence of a conditional expectation that fixes from here to here that fixes a state, and so that's only true if the state has some sort of factorization properties, but that's not true for cyclic and separating states. Yeah, so this is this, and this is kind of a form of mixing, right? So basically what it's saying is that here's my entanglement wedge, here's my causal wedge. If I start with an operator in the causal wedge here, I flow with modular flow, this automolism that holds fixed the entanglement wedge, then I get everything, right? So I can generate everything. It's kind of a form of yes.
So sorry, you said this was used in the proof of 3, but it definitely makes 3 more interesting, the fact that it's true, right? Because this then tells you that...
No, it was used in the equivalence, right? So 3...
Oh, sorry.
3
yes,
implies
yes.
1, 2 comes from this.
Yep.
It's just a condition, right?
Yeah, it's the
In
proof.
the original paper, we had a version of this, but we had to assume some reconstruction as well. So now with this result, you can get around that. So this is some form of mixing. It's like an operator of logicity. And I don't have the time, but it's also a form of, there's a baby version of the time-like truth theorem contained in this. Okay, so I think I'm out of time, but I have much more to say, but I think I'll leave it
keep
there.
talking, then I'm at least going to stick around. I can't speak for everyone else.
I've got nothing better to do.
Feel free to leave, because I understand. Okay, so I'll say a few more things about vacuum plates. This is also new. All right, so I'm going to say something about vacuum codes. What do I mean by vacuum code? So, as Raphael alluded to, this structure really only works if you think about the dual as living on some fixed geometry. And then we talk about quantum fluctuations around that geometry. So let me give a cartoon of that. So if I think about sort of a classical solution to gravity, with AES boundary conditions. And that sort of defines a phase space of the classical theory. So let me just draw the phase space in some arbitrary way. So here's my phase space. Now this phase space is nonlinear because the classical theory is nonlinear. So there's some scale in this phase space associated to the nonlinearities, which goes like 1 over g. And now, so I'm taking g Newton to 0. So in some sense, this sort of nonlinearity is going away. And I'm focusing in on a particular point. And there could be multiple points, but I'm just going to pick one of these points. And then I'm talking about sort of quantum fluctuations near that point. So if you like, some quantum field theory fluctuations. And in particular, because I'm really interested in those fluctuations, I'm setting h bar fixed as I send g Newton to 0. So in particular, you could do this for different solutions and you would get a different code. So roughly speaking, I expect there to be multiple codes for each point in this phase space. And it's a non-trivial problem how you would patch these together. Patch together. In particular, I expect you have to have better control over this one relative expansion to do that. Okay, but this is an open problem. But now let's just focus in on a few points. So on a point. So I want to focus in on the vacuum code where the point that we start off with is just AES. Okay. So study P AES. And then, and in this case, there's a lot of things that we can say about this code. In particular, we can start to get rid of the assumption. So one of the issues with these codes is that we had these causal wedges, but we never knew if we could make an extension to the entanglement wedge. In general, we had to rely on some condition about the relative entropy. I would really like to derive this, right? So I'd like to get this out of something else. So the existence of these entanglement wedges. And so it turns out in the vacuum code you could do that. So I'm going to take, there's a sequence of vacuum states for each n, right? And this is always in my boundary theory. It's always in the boundary theory.
I'm sorry, I think I didn't understand the problem you're setting for yourself. Earlier, I thought you were just defining the entanglement wedge as sort of the largest region you can reconstruct in your sense.
Yeah.
That there exists particular V's and gamma and so on.
Sure.
And so, what was not clear about that you're now fixing?
The maximal extension, whether that exists. And it may not exist. There might be various reasons that it may not exist. But yeah, so the high duality is something that I would like to derive and not put in.
If you put the multiple points, then it doesn't exist, right? Like area operators there. In your case,
that's right. Yeah, exactly. So I'm just going to focus on one.
Yeah. Then it's unique.
Yeah. If I try to patch them together, like make some supercode, then expect it.
But you're not talking about it.
No, I'm not doing it. Okay, so this is a vacuum for each end. It's in the boundary Hilbert space, and the fact that I'm studying this point means that there's a state in the bulk Hilbert space, the beta, that approximates this state. So that means that I think of these. This goes to 0. As what I mean goes to 0. So this looks arbitrarily close to the vacuum of the logic theory. So this is an assumption. This code. This is assumption number 1. And the other assumption.
In reality, wouldn't they often be equal even at finite n? I would have expected you to find VNs where they just equal.
Yeah, by the construction, often it will be equal just because of how you construct it. But it's useful to allow these things just to be slightly more general. And there will be situations where you can sort of derive this and work out.
I was just wanting to check I didn't have
Yeah, I agree. And the other assumption that I'm going to assume is that I'm going to make, which is actually just true, will just be true independent of the code, right? Is that kappa n furnishes a representation of Asymptotically, the conformal theory. A unitary representation, right? So UN of G, say, and it satisfies the spectrum condition, so it has positive energy for the energy on the cylinder. Okay, so that's a natural assumption. That's kind of always true. Okay. Let's see anything else. Oh yeah, and UN, of course, holds things. Then there's a theorem which is a little bit preliminary, but I'm happy to tell you what it is. The following thing is true. There's again an equivalence of statements. 1 implies 2, and 1 is the entanglement wedge for diamonds, boundary diamond regions, is equal to the causal wedge for boundary diamond regions. That's one condition. And the other condition is that H furnishes a unitary representation of Asymptotically conformal, where U of G satisfies this condition. And these are covariant. So, as in, if I take, UN of G, I act on the code, and then I compare that to just acting with U of G, the limit, in the strong operator sense, is 0. Okay, so it acts covariantly through the code. Okay, so these are equivalent statements. So I could have just assumed that the bulk satisfies the symmetries of ABS, in which case I derive the fact that the entanglement wedge of diamonds equals the causal wedge. Or if I wanted to, I could go the other way around, and I can basically reconstruct the conformal symmetries just from this statement. So this is kind of like a mini version of reconstructing the bulk state, because now I know that the bulk geometry, the bulk satisfies this symmetry. Okay, good. Okay, yeah, so there's one more thing that I can say. Someone just has to stop me.
I don't want to stop you, but interrupt you.
Yes, yes.
Because we're talking about this at lunch, but
Yes.
so the entanglement wedge is equal to the causal. So an example where the entanglement wedge is not equal to the causal wedge is like 2 intervals.
Yeah.
But what fails there?
In this, yeah, because this proof heavily relies on symmetries. So it relies on the fact that the modular group for CFT is geometric for a diamond. Okay, so for a diamond, the modular group is this sort of conformal boost symmetry that looks like this. And so knowing that fact allows you to make the statement.
This basically involves just proving that the two causal diamond algebras are commutants, right? The large n.
Yeah, that's right. Yeah,
So
that's right. Yeah. So to prove that nothing is in between.
Well, that's correct. Yeah.
Yeah, and it's a little bit non-trivial, but actually it's based on some old results by Longo and company where they basically did this in algebraic conical theory. They showed how duality follows from symmetries. So yeah, this is how it goes. Okay, so the final thing I want to say is, yeah, so now I want to say something about non-trivial entanglement wedges. This is kind of trivial. This is expected. The result that I'm also going to tell you is kind of expected, but it's something that we can prove now as a theorem. This is also preliminary. If I assume that the limit as n goes to infinity is the partition function of the theory theta h. This depends on n, and it's basically the Hamiltonian on SD minus 1. That's what I mean by that. If I assume that this is equal to the bulk trace of the bulk Hamiltonian, which of course exists as we showed, for all temperatures less than some critical temperature.
So this is you assuming the conditions of the previous theorem for as part of this theorem.
Yeah, correct. I'm assuming either one of these two.
Yeah.
So probably 2 is the reason. So yes, yeah. So for all t, then the first result is the entanglement wedge of 2 diamonds. Just like I said, is equal to just the causal wedge, the algebraic union of the causal wedges of the 2 diamonds. For diamonds that are sufficiently far apart. So here are my 2 diamonds, 1 and 2, with some distance. Then for D is bigger than some number over this critical temperature, then this statement holds. So there's some map between this distance and the temperature that comes from modular theory that allows you to prove that if you have a finite partition function in the limit and it's equal to the bulk partition function, then the entanglement wedge of 2 regions is trivial. Right? So here are my 2 regions. So this is totally expected. If they're far enough away, that's the entanglement wedge. But this is non-trivial because the content, remember, is the entanglement wedge of the boundary region here, and this is a non-trivial entanglement wedge. So this proves the existence of that. So that's the first statement, and then one more, and then I'll finish. Second statement is that the limit n goes to infinity of the mutual information between the 2 regions for the state Vn eta, or actually any state Vn psi, is equal to the bulk mutual information for psi. And again, there's some technical things we need to smooth the mutual information in some way.
And so that's just JLMS combined with the previous state?
It's much more than JLMS. It requires that the split state is in the code. And so actually there's another condition that I did write down, which is intermediate step in this proof that the split state works. But I won't go into the split state. This is what we can derive. Okay, and so we're starting to derive familiar things that we know, but now in a sort of rigorous way. And more interestingly, these codes, I never really said anything about whether the code had a holographic dual. You could easily try to construct this for things that don't have a holographic dual or have some kind of stringy dual. These statements still apply, up to some technical assumptions, but so let me finish that.